Okay, so today we're going to be proving Theorem 1. So Theorem 1 has three parts. The first part says there exists a set that contains no elements. Okay, part 2 says this set is included in all sets. And finally, we are going to say this set is unique. That is, if there are two sets with no elements, they are equal. So they're identical. So there exists a set that contains no elements. We are going to call this set this, or the empty set. So there exists an empty set that contains no elements. This set is included in all sets, and this set is unique. That is, if there are two sets with no elements, they are equal. They're one. So axiom 1, to do this, we're going to use a few axioms. So axiom 1 is simple enough. It says there exists a set. Sets are allowed to exist. Axiom 2 says for each set A equal to another set B, it must be the case that A is contained within B and that B is contained within A. Okay, so if they're equal, they must be contained within each other. And then finally, axiom 3, it says for each set, we're going to say A again, and each proposition, that is P of X, there is a corresponding, proposition P of X where X is an element within A, right? There exists a corresponding set, we'll call it B, that contains exactly and only the elements within A for which proposition P of X is true. Okay, so now that we have our axiom set up, we're going to use these to prove Theorem 1. So we're going to start with part 1 of Theorem 1. There exists a set that contains no elements. So there exists a set. Congratulations, we're using axiom 1 to prove there exists a set. To prove the second part, that this set that we now know exists contains no elements, we're going to use axiom 3. So we're going to choose to use the symbol for the empty set, that is this. So by axiom 3, for each set, the empty set, this is the corresponding set, the idea that for each element within B, it must contain exactly the elements for which B, the elements of B for which P of X is true. And in this case, we're going to say P of X is, it is not the case the elements are within B. So this seems a little bit confusing, but we're able to say that this, again, is P of X. Okay, so we're going to use this to make the claim that the above set, empty set, has no elements. So that is that it can't be the case that there's some element that is within this set, because we know this set's allowed to exist by axiom 3, but we have to prove that there are no elements within it. So to do this, we're going to use contradiction. So by contradiction, we're going to say there exists an element, right, that is an element of the empty set. So going by the empty set we've set up above, there's an element that exists that is within B, and it is also an element that is not within B. Now, this seems like it's not possible, but let's just really solidify it by using an example. X equals -1, and B is a set of every negative integer. So let's try and see if this can be possible, if this contradiction is consistent. So -1 exists within the set of all negative integers. That's true. Ignore my bad spelling of integers, but it's true. And -1 is not in all negative integers. Well, that can't be true. That's a contradiction. So, or an inconsistency within the contradiction. So if the contradiction cannot be true, it must be true that this holds and that the empty set has no elements. Okay, so we're going to put this aside and we're going to prove part 2. So again, part 2 of theorem 1 says this set, that is the empty set, is included in all sets. Okay, cool. So the empty set is in all sets. So we're going to use in to represent all sets. Or every set, however you want to say it. So in is every set. So we're looking for we're looking to prove that the empty set is contained within all sets. That is, all the elements that are within the empty set are necessarily elements in. So by contradiction, we're trying to prove that this isn't true, right? By contradiction, we're saying there exists a set in such that the empty set is not contained within N. So it's not true that for every element X within the empty set, that X is within N. That's another way of saying what I said above. This means also there exists an X as an element of the empty set, and also X is not an element of N. However, in part 1, we just proved that this is not true, right? There is no element X within the empty set because there's no element at all within the empty set. So then we've proven that within the contradiction, there's an inconsistency. Therefore, the original statement must be true, that within the empty set, for every set, the empty set is contained within it. So the empty set is included in all sets. Okay, finally, we are going to move on to part 3 of the theorem. So part 3 of the theorem is that this set, that is the empty set, is unique. So that means that two sets with no elements are equal. And as soon as we say the word equal, we should know exactly what axiom we're going to use to prove this theorem, right? It's going to be axiom 2. So just as a reminder, axiom 2 says that if there exists a set, let's call it the empty set in this case, and it is equal to, we'll call the other empty set D in this case. So if these two are equal, then it must be the case this is contained within D and D is contained within the empty set. Right? So we're trying to prove they're equal and that therefore one, and this is a unique set within itself. So we're going to take first, the empty set is contained within D. Well, by part 2, we already know the empty set is contained within all sets, and D is part of all sets. Right? There exists an element with there exists a set with no elements, empty set, and it's included in all sets. So by part 2, we know that this to be true. Now we're going to look at if D is included in the set with no elements, or in the empty set. Well, we already know that D has no elements. Therefore, it is also in every set, or it's also included in every set or in all sets. So they're the same. The two sets are equal. So with this, we've proven the entire theorem, which I'm gonna bring down and remind you of here. There exists a set that contains no elements. We proved that one using axiom 1 and 3 in contradiction. Then this set is included in all sets. We use contradiction to prove that one as well. And then finally, there is a set, or this set is unique. That is, if there are two sets with no elements, they are equal. And we use axiom 2 to prove equality by part 2.